In my previous video, I had seen what is the adjoint operator and properties of adjoint operator. I had seen this is the adjoint operator. Today's goal of this lecture, today I will see self-adjoint operator. Today's goal of this lecture, today at first I will see what is the definition of self-adjoint operator. Actually, self-adjoint operator is generalized version of symmetric matrix and incomplex Hermitian matrix. Then I will see the matrix representation of self-adjoint operator with respect to orthonormal basis. This is actually the symmetric matrix in real and Hermitian matrix in complex. Next I will see if T is self-adjoint operator, then nullity of T is actually perpendicular of range of T. And when the eigenvalue are real, this is today's goal of this lecture, when actually the operator is self-adjoint, then always the eigenvalue are real. Next goal of this lecture, then I will say when TV is orthogonal to V. When complex inner product space, then inner product TV with V equal to 0, and this is true for all V. And complex inner product space, inner product TV with V equal to 0, that imply the operator T equal to 0. But this is not always true. In real, this is not always true. But if the operator is self-adjoint operator, then inner product TV with V equal to 0 for all V, then that implies the operator T is 0. And this is true for all case, complex, real for all case. Next goal, next I will see when the vector space is inner product space over the complex field, then T is self-adjoint if TV inner product V always belongs to R, and this is true for all V. I hope my all viewers have understood. This is actually today's goal of this lecture. So at first I will highly recommend you please see today's video with pay attention, because this concept actually more important for higher study. Okay? Now at first see the definition of self-adjoint operator. Definition of self-adjoint operator is, if V is finite dimensional inner product space, here field is R or C, then operator T, which map vector space to vector space, is said to be self-adjoint if T equal to T star. That means, in other words, if inner product TV with W equal to inner product V with TW, and this is true for all VW belongs to V. That means, one if T equal to T star, other since adjoint operator means inner product TV with W equal to V with T star W, but here since T equal to T star, that means that imply TV with W equal to V, inner product TV with W equal to V with TW, and this is true for all V and W belongs to the vector space. I hope my all viewers have understood. Let's see the picture. Consider one transformation T from the vector space V to V, and here range of T, which this is the map in range of T, and this is the null space of T, which map to only 0 vector, and this is the null space of T, this is the range of T, and this is be the range T star which is perpendicular to null space of T, and range T star, sorry, here the space is W, here the operator T from V to W, and range T star map to W map to W map to range T star, and orthogonal complement of range T is null T star. This is the null T star, and this is the T, and this part is T star. And in self-adjoint operator, since T and T star both are equal, range of T and range of T star actually same, and null of T and null space of T star is same. And another picture by inner product is, this is V and this is W. Here V maps to TV and this is the W, and W maps to TW, and here the inner product TV with W, this is the small w, and here the inner product V with TW, and actually these both are same for self-adjoint operator. I hope my all viewers have understood. This is graphically, geometrically, and this is actually the by inner product, the picture. I hope my all viewers have understood the definition of self-adjoint operator. Okay? Oh well. Next, in terms of matrices, MT, which is equal to matrix of T with respect to orthonormal basis, and when T is self-adjoint operator, then MT is actually equal to its matrix representation with respect to orthogonal basis is actually equal to the conjugate transpose. That means here A equal to A transpose bar. If this is n cross n matrix, then here actually Aij equal to Aji bar and Aii equal to Aii bar. That means diagonal element Aii belongs to real number. Other Aij equal to Aji bar. So this type of matrix is actually called Hermitian matrix. When the entries are complex, that means when fields are complex. Other, this is called symmetric matrix. When fields are real. When T is self-adjoint operator, then T is actually equal to T star. Then null space of T is orthogonal complement of range of T. We all of us know null space of T is equal to actually the orthogonal complement of range space of T star. But since the operator is self-adjoint operator, that means T equal to T star, then range space of T star is actually the range space of T. So the null space of T is actually the orthogonal complement of range space of T when the operator T is self-adjoint operator. Otherwise, we all of us know null space of T actually the orthogonal complement of range space of T star, but when the operator is self-adjoint, then null space of T is actually equal to orthogonal complement of range space of T star. Now I will say every eigenvalue of self-adjoint operator always be real. When the operator is self-adjoint, that means T equal to T star, and lambda be an eigenvalue with eigenvector small v. Then lambda norm v whole square. This is means actually equal to inner product lambda v with v, and inner product lambda v means Tv with v, and this is equal to, we all of us know, Vt star v. And since this operator is self-adjoint operator, so T star equal to 2T, so this is Vtv, and Tv means actually lambda v, so this is equal to lambda bar inner product v with v, so this is equal to lambda bar norm v whole square. So here I have got lambda norm v whole square equal to lambda bar norm v whole square. That means lambda equal to lambda bar. I hope my all viewers have understood. Since lambda equal to lambda bar, so every eigenvalue of self-adjoint operator always be real. My next question, when Tv is always orthogonal to V. For this, over C, inner product Tv with V equal to 0 for all V. This is only for 0 operator. That means when the field is complex number, then inner product Tv with V equal to 0. If this is equal to 0 for all V, then that implies the operator T is actually 0 operator, and this is true for all V. When the field is real, when F is real, then inner product Tv with V equal to 0. If this is true for all V, then that does not always imply T is 0 operator. For example, if we consider A is this matrix, notice this is actually 90-degree rotation. Here we all of us know this is rotation matrix. If we consider the vector x equal to x1, x2, then Ax equal to 0 plus 1 minus 1, 0, x1, x2, and this is equal to x1, x2 minus x1. And inner product Ax with x, this value equal to x2 minus x1 with x1, x2, inner product, this value equal to x2, x1 minus x1, x2, which is equal to 0. Here I have got inner product Ax with x equal to 0. But notice here the vector is non-zero vector. That means for real Tv with V equal to 0, if this is true for all V, that does not always imply T equal to 0. This is only true when the field is C. In complex field, inner product Tv with V equal to 0, that if this is true for all V, then that implies the operator T is always 0 operator. This is true for all V. But when the operator is self-adjoint operator, when T is self-adjoint, That means obviously T equal to T star. Then inner product TV with V equal to 0. If this is true for all V, then that imply always the operator T is 0 operator. That means in self-adjoint operator, inner product TV with V equal to 0. If this is true for all V, that imply T equal to 0 operator. And this is true for all field, real complex for all field, if T is self-adjoint operator. That means when T is self-adjoint operator, then it does not matter it is real space or complex space. For any space, inner product TV with V equal to 0. If this is true for all V, then the operator always 0 operator. When the field is complex, then if T is linear operator, that means if T mapping from vector space to vector space, then T is self-adjoint if and only if inner product TV with V belongs to real field, and this is true for all V. That means when the operator T is self-adjoint, then inner product TV with V always belongs to real field, and this is actually if and only if condition. Now let's see the proof. At first consider inner product TV with V belongs to real field. That means inner product TV with V equal to its own conjugate, and this is true for all V, and that imply V with T star V, and since this is the conjugate, that means this imply T star V, inner product T star V with V, and this is true for all V belongs to V, and this is true for all V belongs to V. Then that imply inner product TV minus T star V with V equal to 0. And this is true for all V belongs to vector space. If this is true for all V belongs to vector space, then that imply T equal to T star. That means the operator is self-adjoint operator. I hope my all viewers have understood this is. Here one thing noticeable, since TV with V belongs to the real number, so this value of inner product equal to 0, because then we can tell left hand side of equation would be 0, because real equal to complex conjugate, since TV with V belongs to real field, and that imply the operator T is self-adjoint. That means when inner product TV with V belongs to real, then the operator T is self-adjoint operator. Conversely, I will see when the T is self-adjoint, then conversely, if T is self-adjoint operator, then notice right hand side of the equation is 0. That means this imply TV with V inner product is equal to inner product TV with V conjugate, and this is true for all V. Therefore that imply, since this is equal, that imply TV with V belongs to real field, and this is also true for all V. Therefore this is actually if and only condition, and this is our properties of self-adjoint operator. All viewers have understood these all properties. These all properties are very important for her study. So At first, I will hardly recommend you please see today's video with pay attention. Okay? Today, I will stop here. In my next video, I will discuss another operator. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.